Hi, this is Ryan Burt, and I'm going to be presenting my project for EEL6825 Pattern Recognition. My project is on recognizing handwritten digits using clustering techniques. So I'm going to start just by talking about handwriting recognition a little bit. It's extremely useful in current computer applications, in everything from reading documents in. Well, it's probably the main one. But yeah, reading documents and handwritten documents are a huge portion of what we do. So there's a lot of use in getting computers to be able to read those for like checks and legal written documents and even just handwritten notes. Now, even though it's useful, there are a lot of complications today. Handwriting is inconsistent in size, in position with respect to other letters or to like a frame of an image, and even the basic shapes of letters can vary. When you think about even something as simple as the letter A, it can be a circle with a little line, or it can be more triangular. So you can see there are a lot of problems inherent to this. Now, current research into handwriting recognition, a lot of it isn't being done using traditional linear methods anymore, even though they're easy to understand and implement and they're quick. Most of the research today is in nonlinear methods, such as neural networks. Now, these techniques require a lot of processing power and a lot of data, but they can be very powerful and get great results. So, in one example, a paper by Lecoun from France gets less than 1% error on a massive database of letters handwritten on post notes and letter envelopes. Less than 1% error is fantastic for things like handwriting recognition. But the problem is that this system took over 10 days to train, according to his paper. So while it is powerful, there is a drawback in the fact that it requires a massive amount of processing and data and a lot of time invested to get systems like this to work. Now, bearing all this in mind, this presentation is going to propose a new algorithm. It's going to be based on one of those traditional linear methods that's usually seen as outdated, but the advantage to it are it's simple, it's easy to understand and implement, and it's going to work extremely quickly. For that matter, I'm going to take a momentary aside and go and run actually my program to check, and by the time I'm done with this presentation, it will have results. It should actually have results before that. So, as I said, it's going to be based on simple, easy to see features like letter topologies, and it's going to pull features out of that, and then use density clustering, which I'll explain later for the classification. And there's three types of clustering I'm going to use in this, namely the k-means clustering, spectral clustering, and Gaussian mean shift. So to start, I'll talk a little bit about the data set. The total data set consisted of 2,000 images of just handwritten digits like the one you see on the screen there. Now, each image is 28 by 28 and contains every digit from 0 to 9, written in every style you can imagine and varying degrees of neatness or sloppiness. Now, the first step is to process the images a little bit to normalize them, make them as standard as possible, and then extract features. So the first step I did was skeletonization, where I just used a basic skeletonizing algorithm to reduce each letter down to hopefully the basic shape possible. So, as you can see by flipping between these two screens, these were of the same image. That's the original digit right there. And here's the skeletonized image. So you can see it got rid of a lot of extra pixels, things that weren't really needed to convey the shape. Now the point of this is to essentially get rid of the extra pixels, so it's down to the minimum necessary, which usually ends up getting rid of line thickness, and it will normalize size to an extent, at least in terms of the number of pixels in the foreground of the image. Now, once I did skeletonization, the next is to extract features. Now, 1,000 images, each 28 by 28, is a very, very large amount of data, 784 pixels for 1,000 images, which leads to over 7 million data points. So in order to reduce the number of data, we're going to take each of these images and just extract certain features. So then each of the 1,000 images won't have 784 points, it will only have 10. Now the first feature chosen was the total number of pixels, with the thought being that a digit such as a 1 will have less pixels, especially when skeletonized, than a digit such as an 8 or a 9 or a 2 or any other digit. And then you can even think that 8 will regularly have the most, as opposed to something like a 7, which will be on the lower end. So this was just a first catch-all step that was easy and intuitive. Now the next step is to look at the number of pixels in each relative location in a 3x3 box, and there's a couple images on the next slide that explain this better. But one thing I do want to mention is that this will account for translation errors because it localizes the features to the digit itself rather than looking at the entire image. So this is an example of the feature extraction done, where you can see the skeletonized digit and then a box is placed over exactly where the digit is by just searching for the foreground. And then this box is segmented into 9 equal areas, and then the number assigned to each area is the number of pixels out of the total foreground that occur in each. So it kind of looks at this the way a human would look at recognizing a digit, where it looks where the shapes are, essentially, in comparison to all the others, where like a 0 is essentially like a circle, a hole in the middle, right? Whereas a 1 is just a bar. So it would place a major box over the digit and then subdivide the boxes and pull the features out by trying to say where this number has the most pixels. So now we have a feature matrix that's 1,000 images that each have 10 points. So we're going to think of this as 1,000 points in a 10-dimensional space. So each of these 1,000 points has 10 different dimensions to look at. And when you visualize it that way, that naturally leads into the clustering algorithm. So clustering essentially is a way of separating data points into distinct groups by minimizing certain arguments, whether it's the entropy in the data or the distance between all the points in a certain cluster. It essentially takes one of those arguments, attempts to minimize it, and uses that to place them into natural groups. Now, the first method I'm going to use for this is called the standard k-means method. It's a very widely used clustering method, and it attempts to minimize the total distance between each point contained in a cluster. So if you have data in a certain space, you specify the number of clusters you want, such as 10 in this case, for each digit from 0 to 9. And then what it does is it takes each, finds a center, it takes the set, chooses 10 centers, and then assigns each point to the center, and then checks to make sure it's the minimum distance every time. And then continually will update the centers, and then check the points until it can get the minimum distance contained in each center. Now the next algorithm is spectral clustering. It performs k-means, but on the eigenvalues of a similarity matrix between all the points. So it instead performs the clustering on the underlying structure of the data. And here is a common algorithm proposed in a paper that I have referenced at the end. And you can see it takes you step by step through forming an infinity matrix and normalizing it, finding the eigenvectors of said matrix to reduce the data because those describe it. Then you normalize it again and then run k-means on that. And the interesting thing is, when you run k-means on those eigenvectors, as long as you kept everything in the same position, you can take those clusters classifications back to the original data and they'll hold. Now lastly, we're going to look at the Gaussian mean shift, which places a kernel over the distance between every pair of points, as you can see in the equation, and then scales that and shifts it, and shifts the data. Now what this does is it creates a new data set in the end, where the data is shifted to all of its modes. Now, the number of modes found, unlike the other two where you specify you want 10 clusters, in this algorithm, the number of clusters is specified by the number of, or by the size of the kernel. A large kernel will give one mode, where an infinitely small kernel will treat every single point as a separate mode. So now, the training set of the data was used to predefine the centers of the cluster, so it wouldn't retry and find centers every time. And then we went through the test sets and clustered them with each of the three, and you can see the results here. Now, compared to the results I was telling you before with the neural networks getting less than 1% error, these results don't look that good. However, they do pick out certain digits with regularity. I mean, depends on which one. Like k-means is very good at picking out zeros, whereas the Gaussian mean shift is great at picking out ones. And there's enough here to hold promise in looking further into this algorithm. It isn't like random guesses where you'd assume that you'd get 10% of each guess is right. Results do prove that the clustering is working to an extent. Now, the results are poor compared to the neural networks now, but one major plus is that, as I'll show you in a minute, I ran my code during this presentation and got results, whereas the neural network, it would take days to train and a long time to run. And the results may be perfect, but if you need results quickly, a method like this will get you reasonable results fairly quickly. One way this algorithm could possibly fixed is by pre-processing the data more, by doing more than just skeleting, like accounting for rotation, and selecting better features. Even though these ones were intuitive, they may not have been the best ones to actually describe the data. So as I was saying a moment ago, this technique does not account for rotation at all. So say the 1 is on an angle a little bit, instead of all being down the center, now 1 will take place in the corner boxes, which would greatly affect the features, which would cause huge problems in the classification and clustering. So an easy way to get better performance on this, or perhaps not easy but quick, would be to account for rotation issues and try to normalize those. So now, the more advanced algorithms also use a higher number of features and nonlinear methods. So that would be another way of increasing the accuracy of this, but it would probably also increase the amount of time it takes to run. So, in summary, the proposed algorithm doesn't have the same precision, but there are ways to fix it, and it does have the advantage of being much quicker to run. Now, lastly, here are some handy references, some papers covering the neural networks and clustering algorithms that I used in this report. And lastly, we're going to look back at my code, and you can see in that time we came up with these numbers. Now, these numbers I'm showing on my screen right now are actually the percent correct of each digit, going 1 through 9 and then 0. And percent %k corresponds to k-means, spec is spectral clustering, and GMS is for the Gaussian mean shift. Now, you can see here that I have a main script running, and this essentially pulls out the data set, skeletonizes it here, runs through it, goes to a separate file to extract the features, which does the box I showed you about, and then use the training index to specify the center of the clusters we're using, which is this whole section. And then goes down to the bottom and runs the k-means algorithm, just a basic MATLAB code, and then the spectral and GMS algorithms that I coded, and then checks them against the modes of the data and the actual answers given in the data set to check it. So lastly, I'll show you quickly. This is the Gaussian mean shift data set. As you can see, this one's very time intensive. It requires a count or a tolerance to stop. And the spectral clustering, which is quicker, but you can see it forming the infinity matrix here, normalizing it, and then going through the clustering with the start matrix. So this was a quick summary of my project. Thank you very much for your time.